Yeah, hello everybody. Um, we now want to go to the yeah, theoretical or descriptive concept you should also apply in your term papers. So what is understood by Okun's law, and for this we are looking then for data of real growth of the real growth, and we look for data of unemployment, and especially on the dependence between economic growth and unemployment. And for this, we have recapitulated that in general, we have the performance of an economy within the business cycle. So some long-term trend we have already talked about, and that the economy is in general fluctuating with a frequency of 5 to 7 years. This would be one cycle in general around this long-term um, trend. And so we can then, yeah, calculate more or less the actual output relative to this long-term trend, and this we call then potential output, and we define then the output gap as a relative number of actual production minus potential production divided by potential production. Well, and this would just mean that we are above this long-term trend if actual production is higher than potential production, and then this number is positive, and then we talk about expansionary gap, and in the other way we are in a downturn or even in a recession, so we call this a recessionary gap. Yeah, and within these two gaps we have, yeah, where we can more or less identify some costs because of deviating from our long-term trend. And if you remember the concept of this magic square, then we talked about also that the aim is not only as high as possible to push the economic growth, but that yeah, we are not also fluctuating too much about the long-term average, because in a boom phase we would have really, or we should not be surprised if we then have high inflation, and in general high inflation or fluctuating prices means that yeah, we have a high risk where the economy is in the next phase, or in calculating our prices, because we are then in a very risky situation compared to a situation where we have more or less stable prices, and so the economy has costs because of these high inflations. Well, the other way around, in a recessionary gap, of course, in general, there will be much more people unemployed, and unemployment is, of course, also in general costly for our economic performance. And so it is then always very interesting in which phase of the business cycle we are just at some special time. Well, and for this, we now introduced already the connection with the labor market. Then, if we think of that, yeah, the main input within an economy in the production process is, of course, our labor input. Or even in, yeah, a philosophical way, with a Marxian view, you can also say, well, in general, we will have the capital input, but in the end, in order to obtain the capital, just at the end, you still need labor. So labor will be the most important input factor. And then if we say we have some potential output, then more or less we can associate this potential output also with an unemployment situation due to this potential output. And this unemployment situation, which is corresponding to our potential output, we call then the natural rate of unemployment. So all the, so to speak, long-term framework conditions are constant, no short-term fluctuations, but still then we will have some unemployment. Not everybody will be employed in such a situation. And for this, you can also remember your macro course, because there we talked about different kinds of unemployment. And one kind of unemployment was the so-called frictional unemployment, so that there is some yeah, problem in the matching process. In general, your job will be there, but you don't find it, or the company looks for you, but the company doesn't find you. This we called frictional unemployment. And then if we take the yeah, circumstances in which economy is growing, then we have the so-called structural unemployment. And this is maybe the people in your economy does not have the right education for the production process. Maybe they are well educated, but not in that way well educated that they have some abilities we don't need anymore. And this is, well, it could be a problem in the future because of the digital transformation, that many kinds of work we will not need in the future, but of course we will need other abilities in the future. But for this, it could be then the case that we have so-called structural unemployment. So this is meant here that people maybe have not the right skills. So again, we are here then in a more or less neoclassical view of our economy, because all this is coming then from the supply side and not from the demand side, where we say this is more or less then medium-term causes, or even short-term factors we have when we are looking at the demand side. Okay, so then of course more or less we have a one-to-one match between the interpretation of these natural rate of employment relative to the actual rate of employment, because then we can say if unemployment is higher than the natural rate, the relative signs is just in the opposite direction. If the actual unemployment is higher than the natural rate, then we are in the recessionary gap. And the other way around, if the unemployment rate is lower than the natural rate, then we are in a kind of a boom phase, because only some people are unemployed relative to the natural unemployment. Okay, and then we can ask, what is then the quantitative connection between unemployment and economic growth? Because right now we only argued in a qualitative way. For this, we would say, well, economic growth is positively dependent on a lower unemployment rate. And for this, if you remember, in neoclassical theory, when we switched from the Keynesian view, where we talked about the so-called ISLM model, then we introduced the aggregate supply and aggregate demand model, where we had then the AS and AD curve. And then we said in the long run, only these long-term circumstances are relevant for our economic situation. And then we said the long-term AS curve would be then just a vertical line. And this is then only dependent on our situation of our infrastructure, of the situation of our human capital, so the educational system, and so on. And this we could then more or less identify with potential output. And this again is dependent directly on natural unemployment. Well, and Okun just looked then at data of the United States, and what he roughly found is that if the economy is growing with 1% larger than the potential output, that then unemployment falls by 0.5 percentage points. So that more or less the effect is twice as large. So we always need, so to speak, more economic growth in order to obtain the relative a relative high drop of unemployment. So that we have here not a direct one-to-one match between this. What we would at first maybe expect in the long term. Well, and this is just a descriptive empirical situation which we find from the data. And this then we have, or we should try to explain why are firms not directly adjust their unemployment. So if growth is getting higher, why do we not directly then hire new people? And for this, we can say that empirically we find, well, if growth is increasing, then of course it is also reasonable for the companies not to directly hire new people, but just to ask the people who are already in your company, is it possible that you work a little bit more? So maybe overtime, or you have part-time workers in your company so that you just increase labor participation. And especially what we see in developed countries is that if we go back 50, 60 years or so, that we in these times had quite low participation rates, especially from women, and that during time these participation rates slowly increased in the labor market. And well, then this is one of the main explanations that you have not these one-to-one match between economic growth and the natural rate of or the unemployment rate relative to the natural rate of unemployment. Well, and then of course, we can also think of the classical innovation process. We have here a long-term concept, and in the long term, of course, we hopefully have innovations that we are with working the same time have more output. This is what we really hope out of the innovation process. All the invention about machines, or think of the then in the 90s the invention of the internet, and so on, that you really with your time you can create more output. And this maybe we will see in the actual situation a huge impact by digitalization. So this is maybe one of the most important question marks we have. Do we obtain from this digitalization process in the future enough labor for our people? Or does this increase really in a huge amount the productivity so that we need in the future only less people? So this would be then in general explanations why we have not these one-to-one match. So if somebody wants to have a look at the original paper, I will put this then in the Moodle course that you can read these papers. Okay, and now translating this just in a simple formula would then just mean that economic performance relative to potential output, if this has a change of 1%, we should have only a change of 0.5% in natural rate of unemployment, in actual rate of unemployment relative to the natural rate of unemployment. And in order to get here the equality sign, then the estimation says that in front of the difference between actual unemployment and natural rate of unemployment, we need this factor 2, because then 2 times 0.5 equals 1. Or we can translate this in growth rates, and then we would obtain that minus 2 change in unemployment is just the difference between the growth rate, the actual growth rate, and the potential growth rate. And later on, we will then use this version here, or you should use then this version here for your country, and feeding just in the data of real growth and the data of the change of unemployment. And yeah, how we can use this then, this we have already said. I think we can skip this, only to summarize. For this, at a first step, not directly make the analysis, but have only a descriptive look at what we find for the United States. I want to show you the data from 1940s up to today for the United States. And in order that this course is, I think here's my mouse. Yep. This you can see right now. So if you have a larger country, you can also use this data source, which I show you in a minute. this is then the data from the Federal Reserve St. Louis. Maybe I told you that you have a Federal Reserve System in the United States, so you have not only the Fed in New York, but you have also regional central banks, and the Fed in St. Louis provides more or less the data. And where is it? No, it was, then I have to search in another way. Red Excel add-in. Yep. So if you look for this, then here at this page, you can, no, this you don't see. Here it is described how you can download the Excel add-in. And if you have implemented this, I want now to show you how to use it. Then you see up here that, so this is maybe then the starting part. And then you see here that you have implemented this add-in. And this is quite nice. Then you have here international data. There, I don't know, somebody has, I think somebody has Japan. So the guy who has Japan, Australia has also somebody, I think, and Canada too. So maybe you can have also a look here because it's yeah, quite nice and easily you can get the data there. But I want to show you the example for US data. And then we take the real gross domestic product, get data, and then we have here the data quarterly, okay. And what else do we want? Unemployment, labor markets, unemployment rate, and get data. And so we have the unemployment rate now. So you don't need to use quarterly data. Afterwards, I showed you also in an example, which we redo then also for Germany. It's enough to do it with yearly data. But if you find quarterly data, you can just try it. Well, in this here growth version of Okun's law, we find the growth rates here. So if we take yearly data, then we take just the value today minus the value in the former year. Well, if we take quarterly data, then we can also think of what would be the reasonable change number which we should calculate. And if you have quarterly data, maybe you remember this also from your macro course, then we have under yearly fluctuations because the weather is changing during time. And so, in this case, it is then reasonable not to calculate the quarter-on-quarter change, but we just calculate the change of the first quarter with respect to the first quarter of the former year. And so if we do this, then we, of course, oh, here we have monthly data, I see. This M is for month, and this we change in Q. Then it should be quarterly data. Oops. Again. No. So always problems. And let's see if it's worked now. Yep. So, and now he is here. You see directly just averaging the unemployment rate, and now uh, first month, fourth month, we have quarterly data. So then, of course, we have to start with the year 49, because this would be then the first one where we can calculate a change. And then let's take the change in GDP and the change in unemployment. So the growth rate for 1949 would be then 49 relative to the first quarter 48 minus 1, and for unemployment the first quarter of 49 minus the first quarter of 48, and this doesn't look that nice. So, and here let's take in percentage, then we multiply this by 100. So, and this we now take until today. And where we are. Oh no, I have done something wrong. Until 23 is stopping it here. Do we have a change in unemployment? Yeah. Until this. So, and if we plot this, there's my diagram. Oop, again. Yeah. Now I'm a bit puzzled. But where is it? Yeah. Let's try this. Something is wrong with my Excel version. So I close it and reopen it. Let's see. Now, now it's working. Okay. So you see, the main trick is then always shut it down and open it again. So, and what is X and Y? This I always have to look up. So X is F and U is Y. Okay. Mhm. So then we have on the vertical axis the U and on the horizontal axis dy. So, and over the last 60, 70 years for the United States, then what we descriptively more or less see, well, somehow we see here that there is a falling dependence between growth rate and um, unemployment, change in unemployment as we expect it. And what we want to do now is quantitatively, what is the dependence, and now not only until the data of 1960, but until the data of today. Maybe we see then if, from the descriptive point of view, something has changed to the analysis of Okun in the 1960s. Well, and you should then do this for your country from 1980 to 22. Here I described again what you should do then, but before we do this, I will do a short explanation of linear regression with you. So, what we have to do in general is when we when we make a linear regression, we have some data set, and here in this case we take visits of some company in order to sell our product, and on the other time series we have our sales volume, and what we then do is just pointing x is 9, 24, this would be one data point, and then putting all these data points, and hopefully in this case we want to have a positive, or we want to see a positive dependence between visits and sales. And what we then want is to estimate some linear line, which, so to speak, is the best fit of these data points. Well, so we have then to distinguish the dependent variable and the undependent variable. So we want to explain one variable by the other variable. And what we assume in behind is that we have just a linear dependence between these two variables. So what we want to find is just maybe, for example, a linear function like 3 plus 2 times x. Or in general, we are interested in these two parameters, a and b. And for our case, for Okun's law, he found that this parameter b is minus 2. So, but how should we calculate this regression line? Well, as with a business cycle, we have always a gap between the data point and our long-term trend, or here between our data points and the fitted regression line. And this difference we call then the error. So this is our line, and this is our actual data. And what we then do is remember the concept of variance, that we take the difference between the actual value and the value of the value on the regression line, and that we want to try to calculate this regression line in such a way that the sum of all squared distances will be minimized. And the reason for this is, if you remember your statistics introductory courses, that these squared distances are highly connected to the normal distribution. Because remember, normal distribution was described that the density function is roughly x minus xi over sigma I squared. So this is then just our function we have to minimize, and this is then just a function if we put in what is yi hat is just defined by these two parameters, the part of the vertical axis and the slope of our linear equation. So this is then just a function depending on two variables, a and b, because this is known and this is known. Yi and xi are both known. These are our data points. Well, and how do we minimize a function with two variables? What do we have to do mathematically? If you have a function only f of x, and if you want to minimize this, what you are doing? I think this you have very often done in your micro courses. If you want to find the profit maximum, profits are pi p times x minus c of x. What you are doing in order to find the profit maximum. Pardon? Well, if you have here only one one variable, then you do not have to use this formalism of Lagrangian multipliers. What you are just doing. Genau, the derivative. Yes, we just make the first derivative of profits and setting this to 0. And then we, of course, end up with P equals C prime. And this is nothing else like price equals marginal costs. I'm expanding the production as long as the last produced unit, which I sell for price P, just equals my additional costs. Because the first derivative is just the last additional costs for the last produced unit. So this is the mathematics behind it, and it describes more or less a reasonable process in your firm. Well, and if you have two variables, then of course we have to calculate the derivative with respect to A, and we have to calculate the derivative with respect to B, and setting this to 0. So we calculate df dA. Well, what we see is just we have this squared here. And the square, the derivative is just put it in front. So 2 times the sum, because in every part of the sum we have the square. And then yi minus I plus bxi. But this is not the end. We take the derivative with respect to a. And so we have here two functions inside. We have the outer function, this is a squared, and the inner function is this one. And so we have also to calculate the inner derivative. What is the inner derivative of this function with respect to a? So if f of a would be yi minus a plus bxi. What is then f prime? Yep, minus 1, nothing else, because this is a fixed number for you, this is the next number for you, so you have just to calculate the derivative of minus a. So this is minus 1. So I put this minus sign just in front, so we have this condition has to be 0. Well, then the derivative with respect to a, again we have the same. The outer derivative is a 2. yi minus a plus bxi. So, and now we have the function f of b equals yi minus a plus bxi. What is now f prime? Again, think, now this is fixed for me and the a is fixed for me. Yeah? Yes, minus 1 times xi. Definitely, because you have just to take the derivative of a constant times the variable. So minus xi. And also this has to be 0. Well, and what do we have now? Well, within A and B, the variables we are looking for, this is a linear equation and this is a linear equation. Because in general, we know all the data points. These are just numbers for it. Well, and so we have here a linear system, two linear equations with the two variables A and B. Well, two equations, two variables, and from this we know that in general we just can solve this. And this system can easily be solved. This I will not do together with you because you see we have here also the summation signs. Then we obtain quite large formulas. So we only know that this is easily solvable, and I give you then here the solution. If we set in our two conditions, we obtain then this formula here for A, and this formula we obtain for B. And what we also know is that if we take the average of our data set of X and the average of our data set of Y, that also this point is on our linear regression line. And what we then also can show is that if we define the covariance, because now we have two variables, I don't know, have you already talked about covariance in introductory statistics? Hopefully. Yeah. And well, this is nothing else. The variance is xi minus x bar squared, and the covariance is then that we simultaneously look at both variables, so xi minus x times y minus y bar. And then we can formally show that this formula just equalizes to covariance over variance x. Okay, some time is left because then we just want to use our example and just once calculate these linear regression. So you should still see everything. Then let's put this in here. And if we have a look on the formulas, then we see what we need is the sum of all data points of x and of y. What do we else need? We need the sum of the product of both data points. And what we need here is we need also the sum of all x squared. And for this, I already put in here one line for x times y and one for x squared. So if we calculate x times y, 9 times 24, and we need x squared, so 9 squared, and we need always the sums. So here the sum. Oops, in German. Here we need the sum, here we need the sum, and here we need the sum. And then we just put in A. Oh no, we start, I think, with B. B is n times the sum of the product minus the sum times the sum over n times x squared minus x in brackets squared. So how many data points we have? Let's insert another one. So 1 equals this plus 1. So we have 6 data points. So B equals 6 times x times y, this was this, minus sum x times sum y divided by n times now x squared minus sum over x and then outside brackets squared. This is just inserted into the formula. Well, A, we could put in also this formula, or we could also take these conditions, which is a bit faster because we then know that we only have to calculate the arithmetic mean of y and x. So let's calculate this here. So this is then 70 over 6 and 162 over 6. So A will be then, what do we have? Y bar. Oh, this is wrong what I have here. This has to be over A9. So is equal to y bar minus now b times x bar is 3.98. Well, of course, we have also formulas in Excel for this. So this would be then, since it is the slope of our data points, and hopefully I will obtain the same one. Yes, and this is the part of the vertical axis. So we obtain y and x, and then you have it directly. Or what you afterwards in your analysis maybe could do is the quite nice feature. If you plot the data, as we did it for the macro data, unemployment and growth for the United States, then this would be your data, and again, is it in the right way? Let's see. C and D, okay. So this is again oop, y and X, and then you can click in the data. So every data point is marked. Then right click, and then you see that here some menu pops up. In order to that you see this, I put it a bit up here. So right click, and then you down here you have the option trend line. Click on this, and then you have here different procedures of the fitting process. Well, of course, we can think of that our data is not represented by a linear line but by some exponential dependence. But we will only use the linear. So this is already marked. And then we can just give as an output the number of the formula. And later on, we will also calculate the coefficient of determination. What time is it? 22. Maybe we can do it also today. So I will give this also out, and then you have here, of course, the same numbers we have already calculated. And this is maybe the easiest way later on for you, because you have a long time series from 1980 to 2022. So this I will also upload for you later on. So here we have done, or maybe I just put it in here. As an example that you have it too. A and B, copy and paste. And let's put in also the graphics version, the diagram, that you have this too. Yeah, so what we are do here is then nothing else than, so to speak, graphically plotting all these small squares, and then we want to fit in our linear regression line in order that the areas of all these small squares should be the lowest number. Because of course, when we move up this line a bit on the left side, then this would be a bit larger and this will become a bit smaller. And what we then graphically do is, how do we fit in the best way in order to these areas our line. And the funny thing is, if you have not too much data points, if you do it by eye, then you will quite close at the fit you are doing with respect to the square distances. So maybe this is also some biological reason for using the square distance. Because of course we could also think of why not using the distances to the power of force, or the guys who entered my statistic course to use the absolute value of the distances. Okay, so B is then nothing else as than the slope of our regression line and the determines so the effect, though the marginal effect, if I am increasing x by 1 unit, then I know what is the increase of y in this case. And the vertical axis is then given just by the regression coefficient a. So here I gave you already the output of the coefficient of determination, or this, what is behind this is then the so-called correlation analysis. And for this, Bravais and Pearson, I think around 1910, they introduced this correlation coefficient in order to have a quantitative measure, so to speak, how good is my fit? Because of course, this regression here I can do for every data set. This could be also a data set where the data points are dispersing very much around anywhere. And then I want to have a measure, well, is it reasonable that I'm doing this analysis? And for this, we have a look at these covariants. We already have also seen by the calculation of the parameters. And yeah, then we want to have a measure with relation to our linear dependence, which we assume when we make a linear regression. But if we take only this covariance as a measure of dispersion, like we do it with the variance x minus xi minus x bar squared, then yeah, since we have then an absolute number, we don't really know what it means. Especially if we just scale our x and y numbers by 1000, then this number would increase. And for this, we just normalize these covariants up here by the variances of the single parameters itself. And in order to have still the same units, we take here the square root. So this is normalizing the covariance in order to interpret the number for the dependence between x and y. And later on, we will also introduce this number squared, and this is then called the coefficient of determination, because the squared number has also a quite nice geometric interpretation. Well, and then we can say more or less, yeah, if this number r is very close to 0, then we know that all our data points are dispersing very much around, and we are not really sure which linear line should be put into our data. And if this goes then more and more in the direction of plus or minus 1, then we have a highly dependence between x and y. And if it's just 1, then we know that all our data points has to lie on our regression line itself. So if we have here a look at some examples, then I would ask you what would you expect for these coefficients of determination, no, for these correlation coefficients in this case, for the first example. High number or a lower number? Anybody? So maybe here you have some regression line which is quite close at the data points. And then in the neighborhood of 0 or more in the neighborhood of 1. Yep. Yes. So let's see if I can put the numbers quite fast in here, because I feed it in and this I cannot copy. So 2, 3, 4, 5, 6, 7 equals this plus 1 to 7, and this is 8, 12, 15, 16. Oops. 8, 12, 15, 16, 21, 22. And the other example was 24, 9, 18, 24, 9, 18, 8, 19, 8, 8, 19, 8. So let's just plot it. Oh, this you don't see. So going up here. And getting our coefficient. So this would be this one, and also take this one. This I will give you in a minute. Oh, what kind of correlation coefficient you would expect for this one? Maybe we can fit in a line like this. So close to 1. If the data points are quite away from our regression line. More at 0 or more 1? Yeah. Yeah, so it will be quite closer to 0, and we have here also a negative slope, and this was a positive slope. And if we have a negative slope, then also we have to come from the lower part to the to 0. So here some number, some negative number close to 0. Well, and now let's calculate this one also from the graphical version. We have the coefficient of determination, and do you see this? Yeah. The correlation coefficient, we have also a formula. So first one and oops, second part. So here we see quite close with 9.8, and then we can copy this one here, and here we have this minus 0.5. So 0.98, and this one was minus 0.46, minus 0.46. And what do you think would be the R here? If every data point lies on the regression line, then we have a definite dependence between the data points and the regression line. Well, then of course we would have here a 0, a 1, and in the last example, well, here we actually don't know. It's totally symmetrically distributed. So is this the best fit, or is this the best fit? Or would it be this, or would it be this? We don't know. And for this, we more or less cannot determine any dependence between x and y. And so here we would have a correlation coefficient of r equals to 0. Okay, and then we more often use not the correlation coefficient, but the coefficient of determination. And yeah, the reason is we can quite good graphically interpret this. And from this graphical interpretation, we can then say that the number we obtain for the squared correlation coefficient, that we interpret this as if this number is, for example, 0.78, that our model, that these two data points have a linear dependence, is explained by this linear regression line with 78%. And this, I hope I could explain via these diagrams. So the first parameter, if we have a data set, remember your statistics courses, is that we calculate the average. Well, here I just put in the horizontal line of averaged data points of the of our numbers of y. And then we have a distance of every data point with respect to our average. This would be so-called our total distance with respect to our representative of this distribution. And what we are doing now via the linear regression, we more or less move this line a little bit upwards or downwards. And then with respect to the regression line, this data point moves a bit more in the neighborhood of this line. And then we say, okay, this part now, this we explain the difference with respect to the average. This we explain via our linear regression because now we have this sloped line. But then we have still a distance left, and this we call then the not explained distance. Well, and again, then we make the step that we say, well, we want to use these squared distances. So this would be the total squared distance. This would be then the explained squared distance, and this would be then the not explained squared distance. And what we formally can say is, of course, the total difference squared is just the not explained distance squared plus the explained distance squared. And what we then formally can show is that this number squared is just this explained distance squared, and this is the total distance squared. And since this is the case, then we say if this number is 0.7, we say, okay, our model explains 70% of the dispersion of our data set. So now we are running out of time. So the calculation, I think we make then on Monday. Then we will just do the calculation for our example, and in the end I will give a short analysis of US data, and in order that you later on can also do it for your countries, I will do it with IMF data, which you can use in your term papers for Germany. And this analysis you could more or less redo it then with the same IMF data for your countries. So I know that all this is new, and but I think doing some quantitative analysis in your studies would be a good thing, and you are not alone. I showed it. I will show you how to do it. Okay, then thank you very much for today.